Hi guys. So I'm going to try and give you an idea of what this distortion is all about in this IUT papers. In these IUT papers. So first I need to set up some notation, but let me just kind of write the title here. Distortion phenomena. In IUT. Okay, so I just need some setup here. So we're going to take X to be, or let's say F to be, a model Frobenioid. And so it has some divisor function, it has some principal divisors, and it has some div map between them. Okay, and this, again, sits over its elementary Frobenioid. So this is the elementary Frobenioid, and then we have some base category. Base category. Okay, and I want to define the units, so for an element. So let me give some definition. Let me give two definitions. So the first is for, let's say, A and F. We define the units of A to be the endomorphisms. So let's do it like this. Sigma, these are going to be the automorphisms of A, such that the elementary part is exactly the identity. Okay, so we have this elementary part, and we can go there, and then we can ask that it's the identity. The other thing is we can define the monoid of an element, and this is the same thing, but with endomorphisms. All right. So this is the units in the monoid of Frobenius elements. This makes sense. Another construction that I haven't mentioned is that there's a Picard group. So for there is a notion of a Picard group. Let's say okay, and so we'll call it pic F of A, and this is going to be defined to be the divisors modulo the boundaries here. Okay, so here again, phi is phi, and then this thing here, I'm just going to call it P. Okay, so this is the notion of a Picard group. So we have these two things. We have divisors, and then we have boundaries. And I guess maybe I should put a group here. And so this gives us a notion of a Picard group. The last thing I think I need is, do I need anything else? I need, what else do I need? I know I need something else. So I have the endomorphisms, I have this, I have the Picard. So I'm going to come back and do it because I can't remember. So so now I'm going to give a baby lemma. So I'll come back and do it when I need it. So so there's this what am I doing? Oh, okay. So now we're going to go arithmetic. Okay, and so what we're going to do is we're going to take F to be a number field. We're going to take F tilde to be some algebraic closure. And then we're going to let X be here the Frobenioid, the arithmetic Frobenioid, associated to F tilde over F. Okay, and so this was, as we recall, that this thing was built from Arakelov divisors. From Arakelov divisors. Okay, so now we have our Frobenioid here. Oh, okay, I remember what I need. Okay, so the other thing that I need was a Frobenius trivial element. So an element A and F is Frobenius trivial if there exists some phi from the natural numbers, so the under multiplication, to the endomorphisms okay, so there exists some monoid of endomorphisms like this. So okay, so this should be thought of as having you know, a bunch of commuting lifts of the Frobenius. Okay, and if you're familiar with lambda schemes, so this is like a lambda scheme. A lambda scheme. Okay, so this comes from James Borger's version of what a lambda scheme is. So this is okay. So these should be thought of as kind of like lambda elements. Okay, so we have that. Okay, now I'm going to go back to this arithmetic setting, and I kind of want to state a theorem or a lemma. So lemma says the following. It says that so for all x in this arithmetic Frobenioid x, we have the following equalities. So we have that this thing, the monoid elements are the same thing as the unit elements. Let me say that these are exactly equal because one's a subset of the other. And then there's a natural isomorphism to the torsion, so the roots of unity in the field here. One moment, I'm going to cut this out, I'll be back. I'm going to prove the claim that for objects here, here with base at k, that this is the same thing as this, which is isomorphic to this. Okay, so this is the claim. So what is this? So these are really A is really a pair. Let's call it D, where D is an Arith-Kalov divisor. And well, now we need to look at an element here. So let's call it this thing here. So this is so this is an endomorphism. With this part being the identity. And so what does this mean? So phi is, again, it's the elementary part plus this principal divisor. And what is the elementary part? The elementary part is this base map. It is a divisor. And it is a degree. Okay, so this being the identity means sorry, for this part being the identity, this means that this is the identity, this is 0, and this is 1. Okay, and the condition on maps is that they have that Riemann-Hurwitz condition. So it says that f phi star, and then so we had this divisor. Okay, so this was the divisor here, plus the degree, plus the divisor of the map. Okay, this is the divisor of the map, like this. Okay, so this is the condition on maps for Frobenioids. What this is telling us is that we're going to have this equality here, so this is going to be 1. This is the identity, so these two things are going to cancel. This is also going to be 0. Okay, so we get that the divisor of u phi is 0. And so now let's examine what this means. So the divisor, so again u phi is in this principal part of our object, and our object is A. So but this was just K star, okay? And then the value group, so this was this direct sum over all primes. So this is just like the Arithmetic divisors, so Y, we'll just say places. And these were the completions modulo, well, okay, so I'll take the groupification modulo the ring of integers, the units here, okay, and so the divisor map, so we have div phi in here, so this is the natural image, of u phi. Okay. All right. And what this is saying is that so the statement here that this thing be 0 is really saying, so okay, so it's saying that so this is really a multiplicative, right? So this is written multiplicatively. So it's really saying that the image, that u phi is congruent to 1 modulo okv, or ky, sorry, u phi star for all y. Okay, and one can check that this is saying u phi is in sorry, it's the root of unity. Okay. So this goes along with the idea that so when you take an Arkelov, so if this is a metrized line bundle here, so this is defined to be equal to the sections of M. So this is okay. So this is a projective module together with a bunch of metrics, and you define this in Arkelov theory, and then if you take M to be okay with the absolute values, so the standard absolute values that you have given with okay, then you find that this thing is really the roots of unity union 0. Okay, so yeah, that's where this is coming from. I'm going to give a lemma. So this is Mochizuki's baby distortion lemma. And it says the following. So there's going to be, I'm going to do 3 parts. 1, Okay, so let X be an arithmetic Frobenioid of some number field in its algebraic closure. It says that if X in here is Frobenius trivial, then the Picard of the realified X of this Frobenius trivial element after realification is the same thing. So is isomorphic to R via this degree map. So we can take degrees of these Picards and it makes sense. Okay, and this is we have that this Picard group is isomorphic to R via degree, taking R K-love degrees. Okay, so the second fact is so this is the first thing. It says that Frobenius trivial elements trivialize Picard. Okay, the second thing says that if we're going to take two of these guys, okay, so we take these two arithmetic Frobenioids associated to two number fields in two different algebraic closures, okay? And we suppose that after realification, so suppose that we have some map psi from X to R, or so from X to Y, such that this, after realifying, Y of R is an equivalence of categories. So this is an equivalence of categories. Okay? Then, so I'm going to do the conclusion on the next line. Then, so there exists some constant just depending on this, in R, such that for all X in the realified guy, Frobenius trivial, so let me just write down the statement here, so that the degree, the two Arkelov degrees are compatible. Composed with, so there's this Picard, so okay, we take psi of R, we take the Picard so that we have a map between Picards, and this becomes the Picard of Y of R. Okay, so that these things are sense, and so here we should say that Y is this dude here. So let's, I mean, we can take it after realification, doesn't hurt. Which is automatically, so here, this guy here, which is automatically Frobenius trivial. Okay, so I just kind of want to make an observation about what this is actually saying. So what this is saying is that, so we have this guy. I'm going to just omit the reals right now. So we have this dude here. So we have this Picard of some Frobenius trivial element. By the first theorem, it said that we can go to the real numbers by taking this Arkelov degree. Okay, so by the first part. On the other hand, okay, we have this pick functor, but we can take the pick functor of this map here, so the psi. Okay, so in this diagram, again, I'm going to say X is XR, Y is YR, and psi is going to be psi R. Okay, so just to simplify notation, I'm gonna do this. Okay, so here we have pick Y of Y, like so. Okay, so we have two things, and this thing has a degree map. Okay, so under this equivalence of categories, right? It says that okay, we can do two things. We can go here, and then we can go over and trivialize this way, or we can just trivialize using our degree. And it turns out that these two things they're almost the same, and they vary by this constant here. So this is kind of this distortion factor. So this is the distortion. Okay, and this kind of goes into the theme here. So like we have this thing here, and then after realifying here, this is kind of like some sort of symmetry breaking. Okay, and so what you do is you're forgetting structure here, and after you forget, you get some isomorphism, and then what happens is that when you have these, we have these two natural trivializations of these Picards, and that they're both related by some constant distortion factor, and so this is why it's called I'm calling it the baby distortion lemma. I guess I should also label what this is. So this is this for people interested. This is in Frobenioids 1, theorem 6.4. Okay, so that's the second part. I said that there were three parts. The third part is the following. It says that if psi is an equivalence of categories, then this degree map is 1. Okay, so again, if we have it as in part 2, if we started with something that was just an equivalence of categories, right, then there's nothing really going on in this trivialization. It says that, okay, well, this is going to be 1 and they're just going to be the same thing. Okay, so that's what I wanted to say. So let me just say what the proof ideas are. Okay, so the first part, which is the part about the existence of a trivialization. So this is Dirichlet's unit theorem. The second part is it just uses some basic ordering properties. And the third part is so it uses Chebotarev. Okay.